In this lecture, I will discuss with you what is the meaning of cyclic coordinates and what is the physical significance of these coordinates, and I will explain with this using simple examples. So first we will consider the Lagrangian. For a dynamical system, the Lagrangian L is defined as the difference between kinetic energy and potential energy. T minus V, where T is the total kinetic energy of the system, V is the total potential energy of the system. In general, this Lagrangian will be a function of the generalized coordinates Qi and generalized velocities Qi dots, and sometimes it may depend on time also. This Qi I can run from 1, 2, 3, etc. up to n if there are n generalized coordinates. Okay, if you are considering a system of n degrees of freedom, there will be n generalized coordinates, and in general, the Lagrangian can be a function of all the generalized coordinates, all the generalized momenta and time. For example, if you consider a one-dimensional harmonic oscillator, if you are considering a one-dimensional harmonic oscillator, then the Lagrangian is given by half m x dot square minus half k x square. So here you can see that Lagrangian is a function of x dot. Okay, x dot. Similarly, if you consider the case of simple pendulum, then Lagrangian is given by half m L square theta dot square plus mg L cos theta. This is the Lagrangian. So here we can say that L is a function of theta dot. Okay, these are systems having 1 degrees of freedom, 1 degree of freedom. So we will have only one generalized coordinate and one generalized velocity. Lagrangian will be a function of that coordinate and velocity. Okay. Now, suppose one of the generalized coordinate is absent in the Lagrangian. Okay, Qj is absent in the Lagrangian. When Qi runs from Q1, Q2, etc., one of the coordinate Qj is absent in the Lagrangian. Consider one such situation. That is, the Lagrangian can be written as Q1, Q2, etc., Qj minus 1, then Qj plus 1. There is no Qj. And then there is Q1 dot, Q2 dot, etc., Qj minus 1 dot, Qj dot, and Qj plus 1 dot, etc. And there may be dependence of time also in general. So here the coordinate Qj is absent in the Lagrangian. That is why I written like this: Qj minus 1, then Qj plus 1. Qj is absent. Qj is absent. Then Qj is known as cyclic coordinate. Qj is known as cyclic coordinate or ignorable coordinate. Cyclic coordinate or ignorable coordinate. That is the definition of cyclic coordinate. Then what is the relevance of this coordinate? We have Lagrange's equation d by dt of dou L by dou Qi dot minus dou L by dou Qi is equal to 0. Here again I can run from 1 to etc. up to n. So there will be n Lagrange's equations for a system having n degrees of freedom. If Qj is absent in the Lagrangian, then that implies dou L by dou Qj will be 0. Because there is no explicit time dependence of Qj. There is no explicit dependence of Qj on L. Okay, there is no explicit dependence of Qj on L means partial derivative of L with respect to Qj will be 0. So that means from this equation I can write the equation for Qj as d by dt of dou L by dou Qj dot equal to 0. Because this dou L by dou Qj will be 0. So, as per the definition of cyclic coordinate, it is absent in the Lagrangian. So, partial derivative with respect to that coordinate will be 0. So, Lagrange's equation will takes this form. D by dt of a quantity 0 means d by dt of a total time derivative of a quantity is 0 means that quantity itself will be a constant. So, dou L by dou Qj dot will be a constant. Okay. So, this is an important statement. If Qj is absent in Lagrangian, then dou L by dou Qj dot will be a conserved quantity. That is the significance of that cyclic coordinate. Now, that conserved quantity is, we will call it as generalized momenta. This dou L by dou Qj dot is known as generalized momenta or canonical momenta or conjugate momenta. Okay, you can call it as generalized momenta or conjugate momenta or canonical momenta. Now, why it is called generalized momentum? If you consider a free particle in three dimension, what is Lagrangian? Since it is a free particle, potential energy will be 0. There is only kinetic energy, and in three dimension, kinetic energy will be half m x dot square plus half m y dot square plus half m z dot square. This is the Lagrangian for a free particle in three dimension. Now, if I calculate dou L by dou x dot, its value is mx dot. If I take the partial derivative with respect to x dot, it will be mx dot. Mx dot is nothing but m into velocity along x direction, mvx. And it is nothing but ex, linear momentum along x direction. Okay. Similarly, dou L by dou y dot is my dot and it is mvy and it is py. Linear momentum along y direction. The same is applicable for dou L by dou z dot also. So if the coordinate is Cartesian coordinate, if coordinate is a length, then that quantity dou L by dou x dot will be linear moment. It will have the dimension of linear moment. If coordinate is a length, then dou L by dou x dot will be linear moment. Now suppose you consider the case of simple pendulum. If you consider the case of simple pendulum, what is Lagrangian? L is half m L square theta dot square plus mg L cos theta. This is the Lagrangian. Then what is dou L by dou theta dot? It is simply ml square theta dot. This ml square theta dot, I can write it as ml into L theta dot. L theta dot is nothing but angular velocity. So it is ml omega. This is nothing but angular momentum. So dou L by dou theta dot is angular momentum, not linear momentum. It is angular momentum. So if the coordinate is an angle, then dou L by dou q dot. If I denote that coordinate as q, then dou L by dou q dot will be angular moment. So if the coordinate is a generalized coordinate, then I can say that the momentum is generalized momentum. If coordinate is a length, that quantity will be linear momentum. If coordinate is angle, that quantity is angular momentum. So in general, if it is a generalized coordinate having an arbitrary dimension, that quantity is termed as generalized momentum. Generalized momentum. It need not be the dimension of momentum always. Okay, that quantity need not be the dimension of momentum always. It can be linear momentum, or it can be angular momentum, or it can be any other quantity depending on the dimension of this QJ, generalized coordinate. Okay, so I can say that this is a generalized coordinate QJ. In this side we have generalized momentum. I will denote it as Pj, and Pj by definition it is dou L by dou Qj dot. Okay, if I separate these two sides, then for different systems I can write like, if you have these two things, suppose in the first case, suppose Qj is a length coordinate x, then Pj will be a linear moment. Linear moment. Okay. Suppose Qj is theta, an angle. This is length. Second case, if it is an angle, then Pj will be angular momentum. Pj will be angular momentum. If Qj is, say, momentum, if you are considering the coordinate as momentum, then Pj will be having the dimension of dou L. L is Lagrangian. It is difference between kinetic energy and potential energy. So it will have the dimension of energy ml square t minus 2 divided by Qj is momentum. Momentum is nothing but mass into velocity L m L t minus 1. But this is Qj dot. Qj dot. So there will be by time also. That is, this will have dimension of length. This will have dimension of length. All others will cancel. So if the coordinate is having dimension of momentum, its generalized momentum will have dimension of length. Okay. So depending on the dimension of the generalized coordinate, we can have different dimensions for generalized momentum. Okay. I think it is clear. Now, I will give you some examples in order to understand the significance of defining generalized coordinates. Okay, for a particular physical system, if you have cyclic coordinates, then what is the advantage? For that, you consider the case of projectile motion. You consider the case of projectile motion. For projectile motion, the situation is like this. You have a particle which is thrown with some initial velocity and then move under the action of gravity alone. At any instant of time, its coordinates, you can use either the Cartesian coordinates xy, this height is y, and this length is x, or you can use the polar coordinates r and theta, or you can use the polar coordinates r and theta to represent the position of particle at any instant of time t. Now, first you consider the case of Cartesian. First you consider the case of Cartesian. What is kinetic energy? Kinetic energy is equal to half m x dot square plus y dot square. This is kinetic energy in two dimension in the Cartesian coordinate system. What is potential energy? Potential energy is V. It is mgh, and here the height from reference level. This you can take this as reference level, and the height is y. So it is mgy. Lagrangian is half m x dot square plus y dot square, half m x dot square plus y dot square. Then potential energy minus mgy. So I can say that Lagrangian is a function of y x dot y dot. There is no x. So x is absent in the Lagrangian. X is absent in the Lagrangian. So in this particular example, x is the cyclic coordinate. Okay, x is known as or x is cyclic coordinate in this particular example. X is cyclic coordinate. And what is the corresponding momentum? Px. It is dou L by dou x dot, and that is nothing but mx dot. We already know that if a coordinate is cyclic, then corresponding generalized momentum will be a conserved quantity. Okay, x cyclic implies px is conserved. Px is conserved. As you all know, if you take the case of a projectile, it is a particle which is moving under the action of gravity alone. That is the only force acting on the projectile is gravitational force. It is vertically downward. So there is no force in the horizontal direction. Therefore, momentum along horizontal direction is conserved. Okay, this is one of the equation of motion. Now, equation of motion in y. Equation of motion in y. It is d by dt of dou L by dou y dot minus dou L by dou y equal to 0. Here dou L by dou y is mg minus mg because this is a partial derivative of this L with respect to y. So that will give you minus mg. Dou L by dou y dot is my dot. Substituting this back in the original expression, d by dt of my dot plus mg is equal to 0 or my double dot is equal to minus mg. This is one of the equation of motion, and the other equation of motion is mx dot is equal to constant. So these two are the Lagrange's equations of motion. These two are the Lagrange's equation of motion, and it is clear that this is second order ODE. This is first order ODE. Actually, Lagrange's equations are second order ordinary differential equation. But in the second case, since x is a cyclic coordinate, we can do one integration. Okay, what is the one integration? Actually, that equation is d by dt of mx dot is equal to 0. The second equation of motion in x. Since we have dou L by dou x equal to 0, this quantity will not be there. So d by dt of dou L by dou x dot is mx dot. That is equal to 0. If you do one integration, this will result in mx dot is equal to constant. So this process is actually doing an integration. So if a coordinate is cyclic, doing one integration and calculating the first integral of motion is very easy one. Okay. So this is the process of doing one integration, and the resultant thing we obtained is known as first integral of motion. So the resultant is a first order ordinary differential equation. That is the advantage of cyclic coordinate. If you have a cyclic coordinate, doing the or solving the problem is very easy. Okay, one of the integration is trivial. You can get this quantity mx dot is equal to constant. Now, in the same problem, if you consider polar coordinate, okay, in the same problem you can also use polar coordinate for writing Lagrangian. What is kinetic energy? Kinetic energy is equal to T is equal to half m r dot square plus r square theta dot square. This is the velocity in plane polar coordinates. Velocity in plane polar coordinates is square root of r dot square plus r square theta dot square. So half mv square is velocity in plane polar coordinate is square root r dot square plus r square theta dot square. Okay, this is a standard expression. Half mv square becomes this. What is potential energy? Potential energy is V is equal to mgh, and from that figure h is nothing but r sine theta. Okay, you can look at this figure. This y, this is the height, it is r sine theta from this right angle triangle. So Lagrangian is half m r dot square plus r square theta dot square minus mg r sine theta. So I can say that L is a function of r theta r dot theta dot. Okay. there are no cyclic coordinates. None of the coordinates are cyclic. Okay, none of the coordinates are cyclic. But if you choose Cartesian coordinates, x coordinate was cyclic. Okay, here both r and theta is there in the Lagrangian, so there is no cyclic coordinate. What is the equation of motion? Equation of motion in r. It is d by dt of dou L by dou R dot minus dou L by dou R equal to 0. But dou L by dou R is mg with respect to R partial derivative, that will give you minus mg sin theta. But I think there is one more term. This is mr theta dot square. What is dou L by dou R dot? It is partial derivative with respect to R dot. It is mr dot. So if you substitute here, you will get mr double dot minus mr theta dot square plus mg sin theta equal to 0. Okay, this is second order ODE. Second order ODE. It is difficult to solve this equation. It is difficult to solve this equation to obtain the first integral of motion. Now, if you consider equation of motion in theta, equation of motion in theta, that will be d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. What is dou L by dou theta? It is minus mgr cos theta. Minus mgr cos theta. What is dou L by dou theta dot? It is mr square theta dot. So if you take the derivative d by dt of mr square theta dot plus mgr cos theta is equal to 0. This is the second equation of motion. I can solve this again. Mr square theta double dot mr square theta double dot plus 2mr dot theta dot plus mgr cos theta equal to 0. Again, second order differential equation, which is very complicated. Okay, second order ODE. So, for the same problem, projectile motion, when we use Cartesian coordinates, the solution is very easy. Especially one of the equation where the coordinate is cyclic, you already have more simplification. That is, the second order differential equation become first order differential equation. Okay, and if we use polar coordinates for doing the same problem of projectile motion, the equations of motion are very complicated. It is very difficult to solve this for finding r of t and theta of t. R as a function of time and theta as a function of time. Okay, the solution of a dynamical problem is finding the position and velocity in terms of or at a particular instant of time. Okay, solution means finding r as a function of t and theta as a function of t is difficult. But here, finding x as a function of time and y as a function of time, it is very easy. That is the advantage of having a cyclic coordinate. I will give you one more example. Second example is planetary motion. Planetary motion. If you have a planet which is revolving around the sun in an elliptical orbit, if you have sun here and a planet is revolving in elliptical orbit, and suppose the planet is somewhere here at a particular instant, then again we can use Cartesian coordinates or plane polar coordinates. First we will treat it with the Cartesian coordinates. Cartesian coordinates. So you can fix your axis at this point. Say this is x-axis, this is y-axis, and with respect to this coordinate axis you can define a coordinate xy here. Velocity will be x dot along x direction and y dot along y direction. Therefore kinetic energy again I can write it as half m x dot square plus y dot square. Potential energy, since it is a planetary motion, potential energy is minus g mm divided by r, or it is root of x square plus y square. This distance, okay, the distance between planet and sun, it is square root of x square plus y square as per this figure. Therefore Lagrangian is t minus v, it is half m x dot square plus y dot square plus g m m divided by root of x square plus y square. So L is a function of x, y, x dot, y dot. Okay. So there are no cyclic coordinates. None of the coordinates are cyclic. Okay. Now if we find the equation of motion in x. What is equation of motion in x? We have to find dou L by dou x. It is minus gm into derivative of 1 by root of x square plus y square. That I can write it as x square plus y square all raised to minus half. That will be 1 by 2 into x square plus y square all raised to minus 3 by 2 into 2x. So that is nothing but g m m x divided by x square plus y square raised to 3 by. I hope it is clear. Dou L by dou x dot, it is mx dot. Therefore equation of motion is mx double dot minus g m m x divided by x square plus y square raised to 3 by 2 is equal to 0. Again a second order differential equation, and it is very complicated to solve this equation. Okay. What is equation of motion in y? Equation of motion in y. Again it will be the same form, my double dot minus g m m y divided by x square plus y square raised to 3 by 2 is equal to 0. So it is a very complicated equation again. Now if we consider plane polar coordinates for solving planetary motion, plane polar coordinates, then what is kinetic energy? T will be half m r dot square plus r square theta dot square, and potential energy V will be minus g m m divided by r. Therefore Lagrangian is half m r dot square plus r square theta dot square plus g m m divided by r. Therefore L is a function of r dot theta dot. There is no theta dependence. Theta is cyclic coordinate. That is the meaning of cyclic coordinate. The coordinate which is absent in the Lagrangian. There is no theta in the Lagrangian, so it is cyclic. Okay. Now, equation of motion in theta. Equation of motion in theta. We already know that dou L by dou theta is 0 because there is no theta. Dou L by dou theta dot is m r square theta dot. So the equation d by dt of dou L by dou theta dot is equal to 0 becomes d by dt of m r square theta dot is equal to 0. Therefore, one of the integration is straightforward, and that will give us m r square theta dot is equal to constant. Mr square theta dot is nothing but angular momentum. Angular momentum of planet is constant. That is very important information that we can obtain from this problem. Okay. So without solving the problem completely, we obtained an important information of the problem. Angular momentum will be a conserved quantity. So we obtained this information very easily because theta is a cyclic coordinate. The solution, one of the integration is very easy. since theta is cyclic coordinate. That is the advantage of cyclic coordinates. In the previous example also, if you are considering the Cartesian coordinate, since x is a cyclic coordinate, we obtained an important information of the problem, that is linear momentum along the x direction is a conserved quantity. Here again, one of the integration is very easy. So a second order differential equation eventually becomes a first order coordinate. In this case also, for planetary motion, the suitable set of generalized coordinates is plane polar coordinates. The suitable set of generalized coordinates is plane polar coordinates. Because if we choose plane polar coordinate, then one of the coordinate is cyclic. If we choose Cartesian coordinate x and y, then both are present in the Lagrange. Both equation of motions are very difficult to solve. But if we choose the Cartesian plane polar coordinates, then theta is cyclic coordinate, equation of motion in theta will be very simple. We can also calculate equation of motion in R. Equation of motion in R. It is dou L by dou R. We have to find dou L by dou R, and it is Gmm by R square plus mr theta dot square. Dou L by dou R dot is mr dot. Therefore, equation of motion is mr double dot minus mr theta dot square minus gmm divided by r square is equal to 0. Right? I think there is a negative sign here. So this is equation of motion in R. And that is second order differential equation. If R is also cyclic, we will get a first order differential equation. Since R is not cyclic, here the equation of motion in R is second order differential equation. So whenever you have a cyclic coordinate, then the equation of motion in that coordinate will be a first order differential equation, and we will obtain the first integral of motion. Okay, we will always obtain a first integral of motion. That is the physical significance of cyclic coordinate. But that is the physical significance of cyclic coordinate. So cyclic coordinate means a coordinate which is absent in the Lagrangian. A coordinate which is absent in the Lagrangian. That coordinate will be absent, but that velocity corresponding to that coordinate will be there. Okay. For example, in this case, uh, theta is absent, but theta dot is there. Theta is absent, but theta dot is there. Theta is the cyclic coordinate. In the previous example, if you consider the Cartesian coordinate, Lagrangian will be a function of y, x dot, y dot. So x is absent, but x dot is there. This is the meaning of cyclic coordinate, and the advantage is solving the problem will be very easy. So, for solving a problem using Lagrangian dynamics, the aim is always to find a set of suitable generalized coordinates. As I always mentioned, the generalized coordinates, the choice of generalized coordinates is not unique. Number of generalized coordinates is unique, but that choice is not unique. So you can choose different set of generalized coordinates, and one has to be careful in choosing the set of generalized coordinates in which we get maximum number of cyclic coordinates. Okay, we have to choose a set of generalized coordinates such that it contains maximum number of cyclic coordinates. Okay, thank you.